We're finishing up Unit 6 today by talking about Chapter 25. So Chapter 25, again, is only going to be one video, and it's mostly examples. But Chapter 25 is about paired samples and blocks. So we're going to look at flexible schedules. This is just a context for an example. A flexible schedule is when you can choose whether you work 5 8-hour days or you work 4 10-hour days. And if you do work the 4 10-hour days, you might work Monday through Thursday, or Tuesday through Friday, or Monday, Tuesday, and Thursday, Friday. But you work only 4 days instead of all 5. And we want to know if the flexible schedule reduces the demand for resources. So a health department experimented with this idea of a flexible 4-day work week. So what they did is for 1 year they recorded the mileage driven by 11 field workers. So here are our field workers. And for 1 year they worked a normal 5-day work week, and this is the number of miles they drove within that year. Then for 1 year they recorded the mileage that they drove for a 4-day work week. So for 1 year the same people worked only 4 out of the 5 days a week instead of all 5. And then they recorded the amount of miles that they drove in that year. We're dealing with paired data here because each year applies to the same person. So the issue here is that we can't use a t-test to see if there is a difference because the two sets of data are not independent. So we have to do something else. Again, these data are called paired data. That's when two groups represent the same people at different times. Thus, they're not independent because they are coming from the same person. So I drive the same route to school every day. So if we looked at how much gas I spent driving to school if I worked 5 days a week versus 4 days a week, it's not independent because you're looking at me both times. Paired data will always arise when you're comparing something before and after. So anytime you're dealing with a before and after, you're dealing with paired data. We can, however, look at a collection of the pairwise differences. So the pairwise differences is when we take all of these people, Jeff, Betty, Rhonda, so on and so forth, and we subtract. So we took the 5-day work week minus the 4-day work week, and then we get this column over here that is the differences. So Jeff drove 116 miles more during the 4-day work week, but Greg down here drove 3,110 miles less. So 4-day work week worked really well for him. Because we only care about the differences, we just end up ignoring the first two columns. We no longer care about the 5-day and the 4-day. We now only care about this last column right here. Because we're only interested in the one column, that means that we actually will be able to do a paired t-test, which is performed in the exact same way as a one-sample t-test, because we are only dealing with one column of data. However, that test is called a one-sample t-test for means of the pairwise differences. Or you can really just call it a paired t-test and then run it like a one-sample t-test. Assumptions and conditions are different here, though. The first is the paired data assumption. So the data must be paired. So you just have to make sure that you're dealing with before and after, or a pair of data. Then you have the independence assumption. This is completely different because it's actually backwards from what we normally do. Here, we're trying to make sure that the groups are actually not independent, because otherwise then they wouldn't be paired data. So you can only do a paired t-test if the groups are not independent. And then the normal population. This one's the same. The population of the differences have to follow the normal model. So you would actually only be checking the histogram for the differences, not the individual pairs of data, but just the differences between the two. So for the paired t-test, the null hypothesis will be that the pairwise difference is 0. So your null hypothesis is that the mean difference is equal to 0. Then when you calculate your t-score, which is the same thing as the z-score, you have t sub your degrees of freedom, which is again n minus 1 here, because we're only looking at the differences, so we only have one set of data, so we only have one sample size. And that's going to be equal to the mean of the differences. So d bar is the mean of all of the differences minus your null hypothesis divided by the standard error, where again D with a bar over it, there should be a bar over that D, is the mean difference, and N is the number of pairs. And then the standard error is the standard deviation of the differences divided by the square root of N. So really the equations haven't changed at all, it's just we're only looking at the differences. So let's actually do a paired t-test example. We're going to use the context that we were just given for the flexible work week. So we want to know whether the change in schedule changed the mean number of miles driven. So the first thing we do is state our null and alternative hypotheses. Our null hypothesis is that the mean difference is equal to 0. And our alternative, because we're just looking to see if they have changed the number of miles, so therefore it would be not equal to 0. And then we have to check our assumptions and conditions. So the paired data assumption, which states that the data are from the same people comparing their work for 2 years, so it's paired data. Then the independence assumption, the data from the first year to the second year is not independent, again because we're looking at the same people. And then normal, so we have to make a histogram of the difference, and it should be approximately unimodal and symmetric. I did not show the histogram here. It is approximately unimodal and symmetric. You should actually show it. Now that we've checked the assumptions and conditions, we can go ahead and perform the mechanics. So I'm going to recopy down the null and alternative hypothesis. So again, the mean difference is 0, and the alternative is that the mean difference is not equal to 0. So I have to calculate the mean and standard deviation of the differences. So I found that the mean difference ends up equaling 982, and the standard deviation of the differences is 1,139.57. So then the standard error of the differences would be equal to 1,139.57 divided by the square root of 11. And in this case, our degrees of freedom is 10 because it's just one less than 11. So I find my t-score, so t sub 10, showing that my degrees of freedom are 10, is equal to 982 minus 0, because that's my null hypothesis, divided by the standard error, so 1,139.57 over the square root of 11. And then this t-score ends up being 2.86. Now I have a two-sided alternative, so when I draw my diagram, 2.86 would be about here, and then negative 2.86 would be in the bottom. So because it's two-sided, I'm looking for both of those areas. So that gives me a p-value of 0.017. So because that's small, I'll end up rejecting my null hypothesis. So in conclusion, the p-value is 0.017, which is small. Thus, I reject the null hypothesis. There is evidence that a change in work week did lead to a change in driving mileage. So now let's look at intervals for matched pairs. So a paired interval is the mean difference plus or minus your margin of error, where this would be your margin of error, and the t asterisk is your critical value, found the same way that we found them before, and the SE is the standard error. So for example, I want to estimate the mean difference in age between husbands and wives. So I have 10 different couples here, so all of these are the couples, with the husband's age and the wife's age, and then I'm subtracting the two. So I actually have the columns backwards. I did husband minus wife. So a positive number indicates that the husband is older, a negative number indicates that the wife is older. So we want to estimate what is the mean difference in the ages between husbands and wives. So the first thing that we have to do is check our conditions. Again, that is paired data. We are comparing the husbands and wives' ages, so it's paired data because you're looking at each couple as a pair. The independence assumption, the husband's age is not going to be independent from the wife, or the husband is not independent from the wife. And then the normal, you need to make a histogram of the differences. Again, I did not show it here. It is approximately unimodal and symmetric. And again, that histogram is only of the differences. Again, since I've checked my conditions and they've all been met, I can go ahead and do the mechanics. And again, I need to find the mean and standard deviation of the differences. So again, the mean difference in the difference between the husbands and wives' ages is 3 years, with a standard deviation of the differences at 3.94. So the standard error of the differences would be equal to 3.94 divided by the square root of 10. Where again my degrees of freedom is 9, so to find my critical value, I have 9 degrees of freedom, and I want to do a 95% confidence interval, so I could use the table in the back of the book in this case, and come up with 2.262 for my critical value. So then my confidence interval ends up equaling the mean difference of 3 plus or minus my critical value, 2.262, times my standard error, so times 3.94 divided by the square root of 10. And this gives me an interval of 0.18 to 5.8. And then we just have to make sure that we interpret our interval in context. That's very important that we make sure to put everything in context. So in conclusion, our interpretation is that we are 95% confident that husbands are an average of 0.18 to 5.8 years older than their wives. And that is it for chapter 25. We're going to go ahead and do that last example on the back of that sheet tomorrow in class, and I will see you guys then. Have a great night.